Hello boys and girls, so in this video we are going to discuss the pre-lab worksheet for experiment 6, diffractions grating. So at the end of this lesson, students should be able to explain the experiment to identify the diffractions pattern using a diffraction grating and also calculate the numbers of diffraction grating line per unit length. So before we discuss about the questions in these pre-lab worksheets, you might pause this video and read over the lab manual on experiment 6. So you can go through the objective of the experiment, the theory we use for this experiment, and then the apparatus needed for this experiment, and then the procedure of these experiments. Okay, let's discuss the questions in this pre-lab worksheet. Question 1. What is diffraction grating? Diffraction grating is actually referred to a plate of glass with a very close line. Okay, for example, shown in the figure given, whereby it will produce spectrum by diffractions and interference of light. And this is the example of a diffractions grating that we are going to use in the laboratory. So when light, for example, laser beam passes through the diffraction grating, the beam will be diffracted at different angle. Then we will see a series of bright dots on the screen. So question 2, state one functions of diffraction gratings. So the diffraction grating is used to separate white lights into its component color of different wavelength. For example, shown by the figure below. Number 3, can diffraction be produced with white light or only with monochromatic light? Justify your answer. Monochromatic refers to single wavelength. Okay, so diffraction can be produced actually by both white and monochromatic light. However, the monochromatic light is much more intense as it diffracts only one type of wavelength, whereas the white light is much less intense due to the various wavelength it is combined of. As we know, white light consists of 7 colors. So white light has 7 wavelengths. That's why it will be much less intense if compared to monochromatic light. Question 4. Make a sketch of the diffraction pattern that you expect to see on an observation screen behind the diffraction grating. Basically, we will observe a series of bright dots on the screen, whereby we are going to have a central bright with highest order bright dots on both sides of the central bright. Okay, and this figure show you the real observations that we are going to obtain during the experiment. Question 5. If the distance between two consecutive lines of a diffraction grating is 6.71 to the power of -6 meter, we want to determine the numbers of the slit per millimeter of the grating per meter of the grating. Okay, let's go for the question 5a. So we can relate the distance between two consecutive lines of a diffraction grating D with the numbers of slits n, whereby n is 1 over d. So given in this question 5, the d is 6.71 to the power of -6 meter. So we want to get the numbers of slits per millimeter of the grating. So because I want to get the numbers of slits per millimeter, so I'm going to convert the spacing grating or the distance between two consecutive lines. The distance between two consecutive lines, sometimes we also call it as grating spacing. So since we want to find the numbers of slits n per millimeter, So we are going to change the grating spacing, the value of D given, to millimeter. Okay, so 6.71 to the power of negative 6 meter. We change it to millimeter, we have to multiply it with 1000 because 1 meter is equivalent to 1000 millimeter. So I'll get 6.71 to the power of negative 3 millimeter. So then I put it into the equation n equal to 1 over d. So 1 over 6.71 to the power of negative 3. So I get the numbers of slit per millimeter will be 149 line per millimeter. Question B, we want to find the numbers of slit per meter of the grating. So since I want to find per meter, so I no need to do any unit conversion. So D is 6.71 to the power of negative 6 meter. So N is 1 over D. So 1 divided by 6.71 to the power of negative 6. So we will get 1.49 to the power of 5 line per meter. So this is how we relate the distance between two consecutive lines on the grating with the numbers of slits. Then question 6, state the manipulative variable for this experiment. So the manipulative variable for this experiment is the numbers of order n. The responding variable for this experiment is the distance between the spot of order to the center spot L. The constant variable for this experiment is the distance between the diffraction grating and the screen D. The operational definitions that we are going to use in this experiment is the sine theta, whereby the sine theta can be calculated using the equations sine theta equal to L subscript n over square root of Ln squared plus D squared. Question 7, state the hypothesis for these experiments. So the hypothesis for this experiment is the numbers of order n is directly proportional to the distance between the spot of order to the center spot L. Question 8. Why it is important that the laser ray is pointed perpendicular to the diffraction grating in procedure 1? Explain your answer. This is because it will make the diffraction pattern more symmetrically and become easier to analyze the data. Question 9 suggests the best way to measure the length of each respective order of diffraction pattern on the observation screen in procedure 2. So, how we are going to measure the length of each respective order of diffraction pattern? The length here refers to the distance of each respective order of diffraction pattern. So first we will mark the positions of the bright dot using a marker pen. We are going to identify the central bright and then we are going to label it as 0 order for the central bright, and then each of the order follow with the first order, second order, third order, fourth, fifth, sixth, 7, 8, for example. Okay, then after we do the labeling, then we are going to measure the distance from the center of the center spot to the center of the respective end spot. For example, we are going to measure from center to center between the center spot with the first spot. We label it at L1. Then we are going to measure from the center of the center spot to the second spot. We label it as L2 and so forth. Okay. Question 10. Refer to figure 1 above. State the meanings of 300 line per millimeter on diffraction grating in figure 1. So, what is meant by 300 line per millimeter? 300 line per millimeter means that there are 300 lines in within 1 millimeter distance of the grating. So if we have already obtained the reading from the experiment, how we are going to do the data analysis? So question 11, from the operational definitions, state the unit of sine theta n. Justify your answer by deducing the unit of sine theta n in a given equations. So we are going to calculate sine theta n according to the procedure. So is there any unit for sine theta n? So we are going to deduce it. So from the equation given, we know that sine theta n will be the length, unit for length is centimeter, the unit for d squared plus ln squared is centimeter squared, square root, so centimeter divided by centimeter is equal to 1, so there will be no unit for sine theta. So for sine theta, there will be no unit. Question 12. A straight line graph, linear graph was plotted in order to calculate the wavelength of laser beam lambda as shown in figure 1 below. So state the respective for the y-axis and x-axis of the graph for this experiment. So if we refer to the procedure, in the lab manual, procedure 5, we are going to plot a graph of sine theta against n. So it means that the y-axis will represent sine theta and the x-axis will represent n. So how do you determine the wavelength of laser beam lambda from this graph? So if we refer to the equation 6.2 in theory, we can relate sine theta with the lambda, whereby we have sine theta equal to n lambda. So by comparing it with straight line equations, y equal to mx plus c, we know that our y-axis is sine theta, our x-axis is n, so our gradient will be represented by n lambda. So from the gradient, n is n lambda. So we rearrange lambda wavelength. Lambda will be gradient divided by n, the numbers of slit. Question 13. How to determine the numbers of line per millimeter n of the grating B from the second graph by using the wavelength of laser beam lambda from the first graph to fulfill objective number 2 of this experiment. So again, if we compare the equation 6.2 in the theory with the straight line equation, we find out that the gradient is represent numbers of slit n multiplied with wavelength lambda. So if we rearrange the equation, we can determine the numbers of line per millimeter n will be equal to the gradient divided by the wavelength. I repeat, so the n will be the gradient divided by the wavelength. Question 14. List all the precautions steps taken during this experiment. First, we have to ensure the laboratory room is totally dark to precisely observe the diffraction pattern on screen. Second, handle the diffraction grating with care. This is because it is a delicate component. Do not scratch the surface of the diffraction grating or touch it with fingers. Care should be taken that the reflected laser light is unlikely to enter any eye. It is dangerous because it may cause permanent damage to our eyesight. The fourth precaution is always ensure that the incident ray is normal to the grating, diffraction grating, and the screen is parallel to the diffraction grating during the experiment is being carried out. So that's it for our pre-lab worksheet experiment 6. I hope by answering all the questions, you have get the rough idea on experiment 6. With that, I end the videos and I shall see you on next video. Bye bye.